Yeah, so this week's AI seminar, we're joined by Dmitri Gallow. He's an associate professor of philosophy at USC and earned his PhD in philosophy from the University of Michigan. And between now and then, he worked at the University of Singapore, the Dianoy Institute of Philosophy, the University of Pittsburgh, and NYU. And he's going to be talking to us about causation and influence in philosophy. And he's allowed us to interrupt him with questions, and you can post questions in the Zoom chat and I'll raise it to him in the room. So with that, I'll hand it over.
Yeah, thank you so much for having me. Thanks for coming. Give me a second, just pull up my slides. Okay, yeah. So yeah, please feel totally free to interrupt me at any point if you have any clarificatory questions or if you want to object to something that I'm saying, that's totally fine. So what I wanted to do was kind of, instead of talking about some of the small scale stuff that I'm working on, I wanted to just give you a sort of big high level overview of what's been going on in the philosophy of causation over the last 20 or 30 years or so. And in particular, I want to kind of focus on three important developments in the field. Firstly, I think that we've all started to realize more and more that we need to carefully distinguish two different kinds of causal relation. What I'm going to call the relation of causal influence on the one hand, and the relation of causation on the other. It's the first big important development. The second important development, and this is really a kind of cross-disciplinary achievement with people in computer science and artificial intelligence and in philosophy, is a development of a kind of formal framework for representing and reasoning about those relations of causal influence. And thirdly, and this is something that the development of those formal models kind of allowed us to show much more rigorously. There's a sense in which the relation of influence is going to underdetermine the relation of causation. So I can tell you everything that there is to tell about which things are causally influencing which other things, but that will not tell you enough to know which things are causing which other things. So that's the plan. I'm going to go through and just go over those three developments. First, the distinction between influence and causation. Then say something about these models and how we can use them to represent influence. And then I'll explain to you why influence is underdetermining causation. But let me start with the distinction between these two different kinds of causal relations. So here are four causal claims for you to think about. Firstly, how much you water the plant influences how tall it grows. How far you turn the volume knob on the stereo affects how loud the volume is. The battle caused the window to break, and the cotillion's abrupt end was an effect of the window's breaking. These are all four broadly kind of causal claims, but I think there's an important difference between 1 and 2 and 3 and 4. So one difference concerns the kinds of verbs that show up in them. So in 1 and 2, you have these verbs to influence, to affect. In 3 and 4, you have the verb to cause or to be an effect of. And if you permute these verbs, it doesn't sound right. If you put in cause in 1 or 2, say how much you water the plant causes how tall it grows. In ordinary English, that sounds bad. If you put in influence or effect in 3 or 4, the battle affected the window to break, the battle influenced the window to break. In ordinary English, this sounds bad. It seems like they're talking about different kinds of things. There's also a difference in what's flanking the verb. So in 1 and 2, the things flanking the verb are interrogative expressions. Sort of in English, it's a nominalized question. You take a question like, how tall did the plant grow? And then you can turn it into a noun phrase, nominalize it. You get how tall the plant grew. In 1 and 2, the things being related are these interrogative expressions, whereas in 3 and 4, what's being related are noun phrases, happenings like the battle, or noun phrases with infinitival clauses like the window to break. It's different kinds of things flanking the verbs. So the thing I want to say is that the relation, metaphysically, the relation that we're talking about in sentences like 1 and 2 is the relation of influence. And in 3 and 4, the relation that's being talked about is something else. It's this relation I'm going to call causation. Influence, I'm going to say, is a relation between variables. What is a variable? Well, a variable is just the thing that an interrogative expression denotes. So it's the thing denoted by that nominalized question. If you talk to a semanticist or a philosopher of language and you ask them, like, what's a question? They're going to say, a question is just a collection of possible answers, all the things that could be the right answer to that question. Those possible answers are the things that I'm going to call the value of the variable. So for instance, there's the question, how much you water the plant. That refers to a variable, and the possible values of that variable are just the possible answers to the corresponding question. So things like, I watered it with 10 milligrams of water or 20 milligrams, so on and so forth. And in general, if I have a variable capital V and a value little v, then if I write V equals V, that just says that little v is the answer to V's corresponding question. Okay, so influence relates variables. What does causation relate? It's actually really controversial in philosophy. There's lots of fights. Some people think that causation is a relation between events, and then there's fights about what an event is. Other people say, no, it's a relation between facts or true propositions. Some people think that facts just are true propositions. Other people think that true propositions are different from facts. There's a contingent of us who have sort of sprung up over the last couple of years, in part because of the development of these formal models, to think, no, the causal relata, the things that causation relates, are the values of variables, so the answers to these particular questions. I think there's lots of arguments I could give for this third answer, but here I'm just going to take for granted that causation is a relation between the values of variables. So I'm trying to persuade you that there are two different relations here, influence and causation. And there are two reasons I think we've seen already to distinguish them. One, it seems like ordinary English distinguishes them. Two, it seems like they're relating different things. Things being related by influence are different from the kinds of things being related by causation. But I also think they have very different roles to play in our broader thinking about the world. So I think in particular, influence has an important role to play in how we think about the relation of causal control and rational choice. So I think if something is outside of your influence, then it's beyond your control. It's outside of your control. If you have some influence over it, then you thereby have some kind of control over it. And also I think, and this is controversial in philosophy, but I think it's true, that when you're making a decision, you should only concern yourself with things that you might have some kind of causal control over. And you should ignore the things that are outside of your causal control. And so for that reason, I think influence has a really important role to play in how we think about rational decision-making. On the other hand, I think causation has a very different kind of... Oh yeah, of course.
So I guess maybe even in English, right? Like, there's that headline, oh, an asteroid might strike the Earth in 2032, and that might influence human behavior, but we have no control over it really, right? And so I guess it feels like when we think about influence, I don't know necessarily that like we always feel that we have control over those variables that are causing the influence.
Yeah, right. So I think the idea is that the things that I do have influence. And those are the things that I control. Right. Other things might influence me that I don't have control over. So like the asteroid is going to influence human behavior, but human behavior doesn't influence the asteroid. And so the control is running sort of in the direction of influence and not the other way around.
I see. So the asteroid is influencing human. It has control over it, but
yeah. Human behavior is controlled by the asteroid.
I guess, to some extent. And that's sort of like an inanimate, force, right? And so, in some case, like when you think about control, it doesn't necessarily involve volition.
I don't think so. This is controversial too. Philosophers fight about it, but I think like the thermostat controls the temperature. That right. Sounds totally fine to me. So I'm completely happy with dumb inanimate objects exercising control.
Okay.
Yeah, so I think that's the role that influence plays. I think causation has another kind of role that it plays in our attributions of moral responsibility. So when we think it's appropriate to praise somebody, when we think it's appropriate to blame them. I think, you can only appropriately blame somebody for the effects of their choices. You can't blame them for things that weren't an effect of anything that they did. So here's a case where I think causation... Yeah. I want to give a case where causation and influence come apart, and where I also think praise and blame comes apart from control and influence. So here's a case. It's call it assassination. So the US and the UK both dispatch a kind of covert agent to assassinate some foreign president in South America or something. And then the CIA agent sees the MI6 agent giving poison to the president's chef. And upon seeing that, he decides, oh, okay, I'm going to protect my own cover. I'm going to stand down. I'm not going to go through with my own assassination plot, which like involves setting off a bunch of explosives in the palace. So the chef takes the poison, poisons the president's food, the president eats the food, and they die. So here, I think the MI6 agent, given that the CIA agent was there as a backup, there's a way of filling out this case where the MI6 agent has no influence over whether the president dies. No matter what they do, the president's going to die. They're either going to die because they gave the poison, or they're going to die because the CIA agent sets off the explosives. And moreover, like that difference in influence makes a difference with respect to rational choice. If the MI6 agent, if the poison is costly and the MI6 agent knows about the backup CIA plot, then it would be rational for the MI6 agent to not hand over the poison, because they don't have any influence over whether the president dies. And if they care about the president dying and they care about saving money, then it would be rational for them to not hand over the poison. On the other hand, I think that the MI6 agent caused the president to die. The death was an effect of what the MI6 agent did. And I think it's important that we recognize a difference in causation between the MI6 agent and the CIA agent, because it's appropriate to blame the UK, but not the US for the death of the president. There's like lots of things it's appropriate to blame the US for in this case. Like it's appropriate to blame them for wanting the president dead. It's appropriate to blame them for like sending over a covert operative to kill him. It's just not appropriate to blame them for the death of the president, because the CIA agent didn't cause that. Yeah.
So
Yeah.
but they situation in a
Yeah, I mean, I didn't say anything, but we can imagine they have no idea that there's this backup assassination plot.
the outcome.
Yes.
But we're defining influence as something that is factual, that's actually representing what happened. And so they didn't actually influence that because there was this intervener that.
Yes.
Okay.
Yeah, you can be wrong about what you influence. Like I have a thermostat in my office that I'm convinced does nothing.
Oh, yeah.
The first like 3 months I was here, I kept trying to influence the temperature by adjusting it, but it turns out I had no influence at all.
Yeah.
So I was just wrong about that. Yeah, right. Cool. Okay, so that's the end of my brief, that there are these two different relations, causation, influence. It's important to keep them distinct, and they have two different kinds of roles to play. I now want to kind of introduce these models that are showing up kind of more and more throughout philosophy, and I think in lots of other areas too, for representing and reasoning about influence. So I'm going to call them causal influence models. There's particular kinds of these models that are called structural equations models. Some people call them causal Bayes nets. They have other names, but I'm going to call it a causal influence model. There's also, there's a broad family of these kinds of models, and I'm just going to focus in on one particular one. But what I'm going to call a causal influence model has 4 different components. The first is a variable signature. The second is a graph, a directed graph. The third is a probability function. And the fourth is an assignment of values to all the variables in the model. So what I'm going to do in this part of the talk is I just want to go through each of these parts of the model and explain what's going on with them, and also say something about how I think we should sort of think about what the model is representing with each of these components. So the first thing is the signature, and the signature has 2 parts. It has a collection of variable names or variable names, and the second part is an assignment of potential values to those variable names. So I want to kind of just carefully distinguish the variables that are showing up in the signature, which I'm going to call variable symbols or variable names, from variables themselves, which are the things denoted by those variables. Like I said earlier, that a variable is just a collection of possible answers. But this thing in the model, this isn't a collection of possible answers. It's just a letter of the alphabet, typically, maybe with subscripts. But the idea is that that letter is representing or denoting the variable. So for instance, oh, there's a typo. We could use B as a name for the variable who ate the biscotti. The second component of the signature is this function that maps each variable name to a collection of possible values, which are the possible, typically real numbers that we're using to represent the possible answers to the question. So for instance, we could use 1 to stand for James ate the biscotti. 2, why did I have at instead of 8 throughout this? We could use 2 for Alice ate the biscotti. And if those are the only 2 possible answers, then this function, the thing that assigns a range to the value, to the variables, would say that the range of the variable B is just 1 and 2. And the signature just consists of those 2 things. So it kind of tells us which questions the model is considering and what the possible answers to those questions it's taking seriously. The next component is a collection of directed edges or arrows between all of the variable names in the set script V. Just to avoid some kind of irritating complications, I'm going to suppose that this graph is acyclic. We could relax that, but we'd have to say a bunch of extra things. And I want to spend a bit of time thinking about what these arrows in the model represent. And what I want to try to persuade you of is that what they represent are direct relations of influence between variables, plural. So let me go through and explain what I mean by direct, and let me explain what I mean by its influence, plural. So here's a simple case. You've got a variable named D that refers to the variable how far the dimmer switch is rotated, a variable I that refers to how illuminated the room is, and then we have an edge. We have an edge between D and I that says that how far the dimmer switch is rotated directly influences how illuminated the room is. What do I mean by direct? Well, by direct, I think it's just going to depend upon the variables that you have in the model, whether the influence is direct. It's not like in this model, I'm saying there's some weird spooky action at a distance where there's no intervening connection between the position of the dimmer switch and how illuminated the room is. There's all kinds of additional variables you could interpolate between D and I. But I'm not paying any attention to those variables in the model. I'm not asking those kinds of questions with the model. In general, if I could have a model with 3 different variables, A, B, C, the model tells me that A directly influences B, that is relative to this variable set A influences B. B directly influences C. It doesn't follow from that A influences C. Influence is not a transitive relation, but it could be that A influences C. And if we had a model that just had A and C, we could have a direct edge between A and C. So this notion of directness, I think, is actually a relatively superficial feature. It's not like there's anything metaphysically deep about the directness or indirectness of the relation of influence. I said it's a direct relation of influence between variables, plural. Why did I say that? Think about a case like the following. Suppose this is, I'm thinking of the movie Crimson Tide, for people who've seen Crimson Tide. You've got 2 officers on a nuclear submarine, Ramsey and Hunter, and unlike in the movie Crimson Tide, the missiles will launch if both of them give the order to launch. If one of them gives the order to launch and the other doesn't, the missiles don't launch. Then suppose that neither of them give the order to launch. First, I think this is an appropriate representation. There will be a kind of, the causal model of what's going on here will have an arrow between Ramsey and Hunter and whether the missiles launch. But I think in this particular circumstance, if neither of them give the order, then whether Ramsey gives the order doesn't influence whether the missiles launch. Given that Hunter has not given the order, there's nothing that Ramsey can do that's going to make any difference with respect to whether the missiles launch. So, you might have naively thought, oh, the arrows are representing relations of influence. If there's an arrow between R and M, then R influences M. I think not so, because in this case, there's an arrow, and we should have an arrow in the model. That's the right way of building the model. But there is no influence between whether Ramsey gives the order and whether the missiles launch. I think instead, the right way of thinking about it is that R and H together collectively are influencing the value of M. So I think in general, what this model, what a causal influence model is telling you is that there's a collective relation of influence between a variable's parents and that variable. There's another thing to kind of note about this example, which is the relations of influence that they're holding in the model.
Sorry.
Yeah. I think I know it's not like there are people out there directly disagreeing with that. Everything I'm going to say here is going to be controversial. I mean, within philosophy, people disagree about all kinds of stuff. I think that people say a lot of different things about how to interpret the arrows. Some people say they represent potential causal pathways. So like there's, maybe actually there's no causal pathway between R and M, but there could be a causal pathway. And then what they mean by causal pathway is it varies from person to person.
Yeah, I mean, in epidemiology, it's the potential. It's like most often used to represent.
So I mean, I can say. I mean, I do think that if there's a directed arrow between one variable and another, then it's possible that the value of this variable is a cause of the value of that variable. But I think the relationship between the arrows and I guess I think it's not best to think about the arrows in terms of the relation of causation for two reasons. One is that the models aren't going to tell us enough to determine causation. Another thing is that I mean, you can cause by sort of taking a long, complicated route through the graph, but we don't want to have an arrow from the cause to the effect just in virtue of that. I mean, I think it's a heavy-duty interpretive question. So is it accepted? No, but I think it's right. That's I think the right way to think about it.
We have a question in the chat. I don't know if Keith wants to unmute also to add more.
Yes, thank you. So the question I had was, it would seem that this is the limitation of drawing this graph with dyadic links, right? So I can imagine a hypergraph would reflect the fact that we have sort of variables that influence one another, that you have to have both R and H together. Otherwise, it would seem that these links mean two different things. Sometimes they mean a direct impact, and sometimes they mean a direct impact conditional on other variables. So, I mean, I guess it reflects maybe Abigail's question, which I wasn't able to fully hear just because of the limitation with the conference room audio. But it would seem that this would be just a limitation of drawing this with dyadic links. Would you agree?
I guess I'm not sure it's a limitation. I guess I'm thinking there's lots of information being communicated with this graph, and we just have to be careful about the information that is being communicated. I'm thinking what's being communicated is that the value of M is influenced by the values of R and H collectively. But I felt like I didn't follow everything I'm saying.
Yeah, and we could talk about this afterwards, so I don't want to interrupt too much your talk. It was just a matter of, these particular links being multiply defined almost. Sometimes it's R directly affects M, or sometimes it's R directly affects M if H affects M, and maybe other sort of graph structures like a hypergraph would be able to represent that.
I mean, they're kind of like, look, it's a DAG. We can define it, the arrows to mean whatever we want. I'm kind of thinking, I want to understand what the arrows mean in the way that the models are standardly used and deployed. And I'm thinking this is the kind of thing where people would write down a model like this without a second thought, even though there's not any individual influence between R and M. And so I'm thinking the way that the models are typically used, at least by people that I'm familiar with, is one where the arrow is not going to stand for a relation of influence between the parent and the child, but rather it's going to be a kind of collective influence between all the parents.
I see. Okay, thank you.
Okay, thanks. Cool. Let me actually, maybe in the interest of time, I'm going to skip over the path relativity thing. Oh, but I do need to talk about this model. So this is a kind of famous example in philosophy. Well, maybe I'll talk about it. This is a famous example in philosophy that came from Heslow. So let B stand for whether some person, Janet, takes birth control, P for whether she gets pregnant, and T for whether she develops thrombosis. And Heslow is thinking, well, birth control, the idea is pregnancy causes thrombosis, but also the birth control causes thrombosis. So there's kind of one path along which birth control makes thrombosis less likely by making pregnancy less likely, and pregnancy makes thrombosis more likely. But there's another path along which birth control makes thrombosis more likely because it's a potential side effect of birth control that she develops thrombosis. And I think in this kind of case, I can hear both of the following claims as true. Whether Janet takes birth control doesn't affect whether she develops thrombosis. Well, sorry, where I'm stipulating that the probability of thrombosis is unaffected by whether you take birth control, because these two effects along the two different paths exactly cancel out. In that context, I think I can hear both whether she takes birth control doesn't affect whether she gets thrombosis, it doesn't influence whether she gets thrombosis. That can sound true to me. But I also think you can hear it as true to say that whether she takes birth control does affect whether she gets thrombosis. And I think that the two claims are sort of talking about two different relations of influence. One is a kind of net or aggregate influence that birth control has on thrombosis. And the other is a kind of path specific or path relative notion of influence. Along this lower path, whether she takes birth control influences and affects whether she gets thrombosis, even though overall it does not. Okay. The third component of the model is a probability function, a joint probability distribution over the values of all the variables. But I think it's actually a little bit more helpful to think about it as a family of conditional probability functions, or a family of transition probabilities, one for every variable in the model. So for each variable, you have a conditional probability distribution over that variable's values, given the values of its parents. And you can take each of those sort of transition probabilities and build up the joint distribution over all of the variables in the model by just multiplying together all of those transition probabilities. So let me give an example of that. So if you go back to the birth control pregnancy thrombosis example, we could say the probability that she takes birth control is a half. The probability that she gets pregnant, given that she takes birth control, is a fifth. It's not good birth control. The probability that she gets pregnant, given that she doesn't, is 4/5. And the probability of thrombosis, given birth control pregnancy, are given here. And once we've kind of specified these transition probabilities, the model is able to generate the entire joint distribution over all of the possible variable values. So those are just all the different rows in this table are different variable assignments to these three variables. And so the thought is pick one of them. You want to know the probability that she takes birth control, gets pregnant, and has thrombosis. Well, that's just the unconditional probability of birth control, which is a half, times the probability that she gets pregnant, given that she takes birth control, which is a fifth, times the probability that she gets thrombosis, given that she takes birth control and she gets pregnant, which is 60%. And so overall, the probability that you end up here is 6%. Cool. Let me actually skip past this minimality assumption. And the final component of the model is just a variable assignment. And I think this is something that's relatively non-standard. I think a lot of people want to define causal influence models without a variable assignment. But I think it's important for the reason that I brought up earlier, which is that whether we have influence between variables is going to depend upon which values those variables take on. So, in the case of Ramsey and Hunter in the missile launch, if neither of them give the order, then whether Ramsey gives the order doesn't influence whether the missiles launch. But I should have done it the other way around. If Ramsey gives the order, then whether Hunter gives the order influences whether the missiles launch. So if you want to look at this model and figure out which variables are influencing which others, I think you need to know something about which values the variables actually take on. And so I think we need to include that information in the model before we say things about influence. Okay, so that's a causal influence model. It has a signature, a graph, probability function, and an assignment of values to the variables. If all of the transition probabilities are deterministic, then you don't have to use a probability function. You could just write down a system of equations. So like in the case I was talking about, all of the probabilities were just 0 and 1. You know, given that Ramsey and Hunter both give the order to launch, the missiles will certainly launch. Given that one of them doesn't, they will certainly not launch. So we could just write down that whether the missiles launch, I mean, these are all binary variables. They take on the values 0 and 1. Whether the missiles launch is determined by whether Ramsey and Hunter give the order, and they will launch exactly if both Ramsey and Hunter give the order. So this is a kind of just, I take this to be a more concise way of writing the information you could have given with this family of transition probabilities. In that special case where it's deterministic influence throughout the model, I think it's typically called a structural equations model. And it's just what you get if you take causal influence model and replace the transition probabilities with equations. Okay, so that's my high-level summary of what these models are and I think how to think about them. And I now want to try to persuade you that the relation of causation is going to be underdetermined by the relation of influence. So if you have one of these models, and in this part of the talk, I'm just going to use structural equations models because the probabilities aren't going to be super relevant. If you have one of these models, you don't know enough. Even if you know the model sort of perfectly, accurately describes the world, you're not going to have enough to say which variable values are causally related to which other variable values. You need some additional information. And I'm going to argue for that by giving you a pair of cases where I'm going to say that those pair of cases are both correctly modeled by one and the same causal influence model. So everything, there was going to be one model where everything it says about influence in this case is true of the things that it says about influence in this other case. But in the first case, the variable value that gets represented by C equals little c is going to cause the variable value represented by E equals little e. But in the other case, that's not going to be the case. There's not going to be causation. So we have two situations that are isomorphic when it comes to influence, but differ when it comes to causation. And so I'm going to conclude that causation is underdetermined by causal influence. Okay, so the first case I want to look at is just the case of assassination that I introduced earlier. And here, like I said earlier, I think it's important to say that the MI6 agent giving the poison caused the president to die. It's appropriate to blame the MI6 agent in a way that it's not appropriate to blame the CIA agent. The other case that I want to look at, oh, sorry, first let me say how I'm going to model this. So I'm going to use 4 variables, M, P, C, and D. M represents whether the MI6 agent gives the poison. P represents whether the chef poisons the president's food. C represents whether the CIA agent ignites the explosives. And D represents whether the president dies. These are all polar questions. The possible answers are yes and no. And so I'm going to represent it with the values 1 and 0. And then I think we can write down these equations that say, well, what the president is going to die exactly if either the CIA agent ignites the explosives or the chef poisons the food. The CIA agent is going to ignite the explosives exactly if the MI6 agent doesn't give the poison. Chef is going to poison the food exactly if the MI6 agent does give the poison. And in fact, this is sort of the exogenous probability assignments. It's just one that in fact the MI6 agent does give the poison. So that's the first case, and that's the causal influence model that we have for it. The second case, I'm going to call it tornado. You're in Kansas, and there's a tornado approaching the farm, and Auntie M sees it coming, and so she runs down into the storm cellar, and the tornado comes by and destroys the house, but because she's in the cellar, Auntie M survives unscathed. In this case, it seems to me that the tornado did not cause Aunt M to survive. It would be weird if Aunt M were to think like, oh, thank goodness there was a tornado because now I've survived. You know, you don't want to praise the tornado for the survival. This seems incorrect. So I'm going to model this case with 4 variables: whether there's a tornado, whether Aunt M is in the storm cellar, whether the house isn't destroyed. So this is, I'm going to use a slightly weird variable here. So this is asking the question, was the house not destroyed? And a value 1 is answering, yes, it was not destroyed. And a value 0 is answering, no, it wasn't not destroyed. And then S for whether Aunt M survives. And then we can write down these equations. Aunt M is going to survive just in case the home is not destroyed or she's in the cellar. The home is not destroyed just in case there's not a tornado. She's going to be in the cellar just in case there is a tornado. And in fact, there is a tornado. And I should say, I mean, in any real world version of this case is going to involve some kind of indeterminism. But I'm thinking we can imagine that all of these equations are sort of perfectly deterministically true. Set things up so that the tornado is only going to take a certain path. Set things up so that it's certainly heading towards Aunt M's home, and she's certainly going to die if it hits, and so on and so forth. Now, this structural equations model for tornado is just isomorphic to the structural equations model that we wrote down for assassination. We can map T for tornado to M for whether the Mi6 agent gives the poison. We can map D star to C. We can map C to P and S to D, and we have exactly the same variables. The corresponding variables are taking on exactly the same value, and they're related by exactly the same, they're related by exactly the same equations. So they're just isomorphic models in these two cases. But in assassination, the Mi6 agent giving the poison caused the president to die. In tornado, the tornado didn't cause Aunt M to survive. They're both correctly modeled by isomorphic structural equations models or causal influence models. So I conclude you can't determine facts about causation from a correct causal influence model. Okay, that's my argument. You could object to P1 or P2. I'm not going to object to them. I take it that like I'm very happy with these judgments. I think that it's the kind of thing where if I start denying that, I lose my grip on how to start theorizing about causation in the first place. I mean, methodologically, I think I try to figure out what kind of thing causation is by starting with some kind of paradigm judgments of instances of the causal relation. And I try to build a theory around that. And both of these strike me as just very, very central core paradigm instances of the causal relation or the lack thereof. That like, yeah, the tornado didn't cause Aunt M to survive, and that the Mi6 agent providing poison did cause the president to die. You could object to P3, and this is an approach taken by philosophers like Jonathan Schaffer and a few others. But I kind of feel like, so the thing that Schaffer says is, well, we need some additional variables in one of these cases to sort of get a model that's good enough, that's going to reveal which variable values are causally related. But I feel like this approach, I'm not optimistic about this approach, because I think that there are very, very simple systems that we can write down, we can imagine, you know, that have very, very similar structures and are represented by exactly the same structural equations models, where we can just stipulate there are no missing variables. So here's a system like this. This is a neuron system, and I just imagine like a very, very simple world that only consists of some neurons that are connected to each other in a certain way. And they can either fire or not fire at certain times. So here, this is a neuron, the one that's I've labeled M, and it can fire or not fire at T1. And if I've colored in the neuron, then it fires at T1. And if I've left it uncolored, then it doesn't fire at its associated time. And these connections the arrows are stimulatory connections. So if the variable at the base of one of these arrows fire, then the one at its head will fire at its designated time. And this is an inhibitory connection. So if the variable at the base of an inhibitory connection fires, the one at its head will certainly not fire, even if it's stimulated by another neuron. So here you have two neurons fire. C does not fire because it's inhibited by M. P fires because it was stimulated by M. And then D fires because it was stimulated by P. This is very similar to the structure of assassination. It's what a philosopher calls a case of preemptive overdetermination. It's overdetermined because these two neurons together make it so that either one of them firing would be enough for D to fire. If M didn't fire and this one did, then there would have been a causal pathway running along here. But in fact, M sort of preempts that causal pathway, it breaks it, and then initiates its own causal pathway that leads to D firing. I think this is very similar to the case of assassination. And kind of by stipulation, the only relevant things here are these neurons and the connections between them. So I think that the structural equations model I wrote down for assassination, maybe it doesn't correctly model assassination, but it had better correctly model this system, because it's just, I've simplified everything down just by stipulation. And I'm also perfectly happy with the judgment here that M's firing caused T to fire. here's a different kind of neuron system. Like everything means all the same things here, but here sort of T fires, and that causes D star and C to fire. And then D's firing kind of threatens to make S fire, but C's firing inhibits it. And in this case too, I feel like T's firing didn't cause S to not fire. Along this path, T sort of created a threat to S, but along a different path, it neutralized that very threat. So it looks to me like T is both not making any difference to whether S fires, so there's no influence, but also there's no causations. T's firing didn't cause S to fire. But these two systems are isomorphic. I can write down the same structural equations models that I wrote down before, and they'll model these very simple neuron systems, where by stipulation we haven't left anything out. So I'm not persuaded by that way of responding to P3. And so I think I just accept the conclusion. I think that you can't determine facts about causation just from looking at what's written down in a correct causal influence model. And there's a kind of question then about like, well, what is the missing factor? Like, we need to know more than we have in a causal influence model, and what's the extra thing that you need to know? And I think a lot of people have thought the missing information is something about what the variable values are representing. So a bunch of people have thought that it matters whether a variable value is representing a kind of default or inertial state of nothing happening, or whether it represents some kind of non-inertial deviation from inertial behavior, so representing something happening. And I think if you go back and look at these neuron systems, that way of diagnosing the problem becomes very, it kind of jumps out at you, because you're like, well, what's the difference in these very simple neuron systems? It looks like the only difference you can point to is like, well, here something's happening, something is firing, whereas here something is not happening, it's just remaining dormant. And so the variable value sort of C equals 0 is representing the default state of nothing happening, and C equals 1 is representing this kind of deviation from the inertial behavior of the thing firing. And so I think this is one of the sort of biggest ideas in philosophical thinking about causation over the last 15 years, is that we need to start paying more attention to that kind of distinction between which variable values are default or inertial, and which represent a kind of deviation from inertial behavior. And there's lots of controversy about how to understand that distinction, and lots of controversy about how it fits into our theories of causation. But I think more and more of us are sticking that ingredient into our theories. And that's everything that I have to say for myself. So thanks for listening.
So like in the MI6, the assassination example,
Yeah.
if you were to say like the inertial state of the MI6 assassin is to provide that poison, are you saying that there's like he's less of a cause, less of an influence?
Yeah, I guess the idea is that giving poison to the presidential chef is something happening. It's not the default state. And then that's the way that we think about it. And if you ask me like, well, what if we thought about it differently? Unclear, because I think we just do think about it as that's the thing that's happening. That's some kind of deviation. Like the default state would be just sitting around and twiddling your thumbs and doing nothing.
So maybe the default state of the chef is to take whatever he's given and to pass it along, like it's a functional default. Like he could.
Yeah.
But I guess you're defining based on the function.
I mean, Joe Halpern, for instance, says that it's always more default for variables to satisfy the equations than to not satisfy the equations. I think that's wrong. But he would say, yeah, then it's default. If this guy's following the equations, then it's default. I think that's not the right way to think about it. I think the right way to think about it is, no, he's poisoning the president's food. Like that's a departure from normal behavior. That's something deviant happening. So I think what's going on here is you have sort of deviant, 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 default. I think the ones are corresponding to deviations, and this is, whereas in the tornado case, the tornado is some deviation. It's something non-inertial, it's something happening. Running into the storm cellar, that's something happening. This kind of weird variable, D star, that's representing the home being destroyed, and that's something happening. And that's, and then survival, this is the default state. She's just continuing to live.
Mhm.
And so the asymmetry, the reason that the isomorphism breaks down is that C is representing a default state in the case of assassination, but D star is representing a deviant state in the case of tornado.
Yeah, I was gonna ask when you were going through the examples, if we switched the kind of outcomes, how that would affect things, but you kind of define this framework around, it's not that outcomes, it's, you know, it's not what they represent, it's not the 1 or 0, it's the, what it, you know, whether that was a new action or not, or a new state, I guess, a change in state.
Yeah.
Can you define that more clearly? Like inertial in the case of survival versus death from assassination.
Yeah.
Yeah.
It would be nice to give a definition of this distinction. But I mean, I could give you some, and then I could counterexample the definitions that I've given. So I know, for instance, it's not just changes in variable. That seems wrong to me. So it's a very natural first thing to think is like, oh, what's going on is that these variables represent changes in the state of the world. Why do I think that can't be right? I think it can't be right because when I think about these models, but I just imagine them continuously firing, it doesn't feel like it makes it, it still feels like if this is just, you know, forget the times that like it's firing at this time, this is just constantly firing. Therefore, this is constantly firing. Therefore, this is constantly firing. It still feels like this guy's firing is causing that guy to fire. Whereas here, if they're just constantly firing, it doesn't feel like this guy's firing is causing this guy to not fire. It doesn't, the judgments don't feel like they change when I turn it into a dynamic case to a static case. So it doesn't feel to me like it's just a matter of changes. It feels like that we have some way of like dividing the world up into, this is the way that the philosopher Tim Maudlin puts it, is that we think of the world as like what he calls a quasi-Newtonian system, where there's like inertial behavior and then non-inertial behavior, right? And that plays an important role in Newton's theory. The thought is, in our thinking about causation, there are certain kinds of inertial things and there's certain kind of non-inertial things. And you can just have a continuous non-inertial behavior. It can just keep being non-inertial. It can keep being deviant, or it can just remain default. But I think that, yeah, I don't want to understand it in terms of changes. Yeah.
And I guess like that example you gave, I imagine you have some familiarity with all the work people do in causal estimation, where they're trying to build this network. And, you know, there is the question of how much data do you need to observe? And given the data you have, there's the question of identifiability, right? So you might have two different models, and given the data you have, you can't tell the difference between them. It sounds kind of like what you're describing is that it really, I mean, I guess in a lot of this, you're not really talking about observation, but from the computer science perspective, when people are doing causal estimation, it's all about using observational, you know, data to determine what the structure is, what those arrows are, right? So, can you speak to that, reconcile kind of the two perspectives that these communities might have?
Yeah, I mean, I just think there's a question about, well, what is the model representing? And there's a question about, like, what is it saying about the world? And then how do you discover whether that thing that it's saying is true or not? And I think you use things like the causal Markov condition or deseparation to try to learn, like the model is going to make predictions. I think I had a slide about the causal Markov condition and deseparation, but I cut it in the interest of time. But right, the probabilistic model is going to make predictions about which kinds of correlations you should see in the data. And then you check to see whether those predictions are accurate or not. And then if they're accurate, you take that as some reason to think that the model is true. If they're not, then you take that as some reason to think that the model is false. But I think that kind of epistemic question, the question of how do I come to learn this thing, is different from the question of the metaphysical question of like, well, what is the theory even saying in the first place? And the question that I'm focused on here, which is different from the kind of causal inference question, it's like, well, what is the model even saying in the first place? Before we try to figure out whether what it's saying is true or false, what would it even be for that model to be correct?
Yeah, so maybe that feels like the heart of this talk, right? And so I guess from a very pragmatic perspective, if I can draw a diagram and for any assignment of variables, give you a result, Auntie M is alive and well or dead, like who cares about causation and influence if we can give the answer, right? And that's sort of like the very dumb view of this. So like what by enhancing this sort of metaphysical sense of influence and causation, what can we do that goes beyond just, inference and prediction?
Yeah, well, I mean, you might want to know who's legally liable. So you've got a model, and I can say exactly what happened and what would have happened under various kinds of interventions, or what other kinds of things, what probabilities we attach to different outcomes. But then you go into a courtroom, and you want to know, like, is the company liable for this? Should this company be held responsible for this thing? And one of the things that the court cares about is the relation of causation. And I think that the court should care about that because causation is intimately related to blame and responsibility. So is the responsibility going to fall on the US or the UK in the case of assassination? And being able to say that is going to require you to think about causation. It's not enough to just say, oh yeah, well, if the MI6 agent hadn't done it, then the president still would have died. That doesn't settle the question of whether he caused it.
Or it's like when you know that the causative factor, then you can intervene and impact that in the health example, and then
The birth control.
the brain example. I mean, that if you understand that structure, maybe there's some kind of therapy that can be implemented based on what the causative factor was, or that would be targeted.
Yeah. Although I think that's also going to, because I can say something, I didn't go over this in the interest of time, but like, yeah, you get to say things in these models about like, well, what would have happened if we'd intervened on pregnancy without affecting birth control? And then you can say those kinds of things without saying anything about, without needing to say anything about causation.
Right.
And so I mean, I think I just agree, if you don't care about causation, like you don't have to care. I think you kind of should care because of its relation to moral responsibility. I think you should also care because it's importantly related to explanation. So I think if you want to know why the president died, pointing to the CIA agent is getting something wrong. The president died because of what the MI6 agent did. And so in explaining why you got a particular outcome, I think you need to pay attention to causation.
Basically, like, it seems like you're saying, because I think there are so I work with it, we are looking for like the explanatory model versus the predictive model, right? And so there's maybe that's like a really relevant distinction, but for a lot of like, I guess it depends on like how causation is being used in the scientific model, right? In the research, like what's the role of causation in the research question? That distinguishes whether or not it's important to consider these factors.
Yeah. Or like, I mean, just a kind of case that's maybe more in your wheelhouse is sort of like you've got some algorithm and it's like giving a certain verdict about whether or not somebody should be let out on bail or whether or not they should be given a home loan. You might want to know, like, was race something that caused that decision? And you could look at the kind of counterfactual variation from the inputs to the outputs, but that's not going to tell you whether race was explanatory. It's not going to tell you whether which factors were explanatory in the output of that algorithm.
Yeah, if anyone in the chat has like a question, if so, ask them, but in the room if anyone. No one's popping up in the chat, so I think we can sort of end here.
Thanks so much for coming.